The rate of a reaction is often, but not always, dependent on the concentration of one or more of the reactant molecules. A rate law is an equation relating the concentration of reactants to the rate, assuming that the reverse reaction is negligible. For a reaction where A is forming products, the rate law would have the form given below, where the rate is equal to some K times the concentration of A raised to the power of N. And N has to be determined experimentally. N is called the order of the reaction, and usually it's an integer that determines the rate dependence on reactant concentration. You rarely see situations where it isn't an integer, but we are going to see a situation like that in the examples. K is the rate constant, and that's just a proportionality constant relating the rate to the concentration to the power. Let's get a little terminology out of the way before moving on. The exponent on each reactant in the rate law is called the order with respect to that reactant. The sum of the exponents on the reactants is called the order for that reaction. In the rate law, where the rate is equal to some K times the concentration of NO2 raised to the power 2 times the concentration of O2 to the first power, we say that the rate is second order with respect to NO and first order with respect to O2 and third order overall, because when we sum the exponents we get 3. Let's consider the organic reaction where we have chloromethane plus hydroxide yielding methanol plus chloride. Experimentally, the rate was determined to be equal to some K times the concentration of chloromethane times the concentration of hydroxide, both raised to the first power. So we would say this reaction is first order with respect to chloromethane and first order with respect to hydroxide and second order overall. If a reaction is observed to be zero order, then the rate of the reaction is always the same, and doubling the concentration of the reactant has no effect on the rate. If a reaction is first order, the rate is directly proportional to the reactant concentration, so doubling A will double the rate of the reaction. If a reaction is second order, the rate is directly proportional to the square of the reactant concentration, so doubling A will quadruple the rate of the reaction. Here we see some different rate equation graphs for A is forming products. On the left, what we're observing is the concentration of A beginning at 100%, which is represented as a 1 here, and then as the reaction proceeds in time, the concentration of starting material decreases. Okay, no more reactant is being added. So we see that for a zero order reaction where the rate is equal to some K times the concentration of A to the 0 power. Anything to the 0 power is just 1, so the rate is just equal to K. And therefore we see a steady decrease, a linear decrease in concentration over time. For the first order reaction, we see that the rate is equal to some K times the concentration of A to the first power. So if we doubled A, we would double the rate. And so what we see here is that we're starting with a certain amount, we could say 100% of our starting material, but as the concentration begins to level off, then over time also the rate of the reaction slows down. In the next example, we have a second order reaction where the rate is equal to some K times the concentration of A squared. So if we doubled A, it would have the effect of quadrupling the rate. And we see that demonstrated here in a more curved graph. So it's exponential. And what we see is, as we're starting with 100% again, and the concentration, as the concentration falls off, the rate slows faster because this is a second order reaction and the rate is more dependent then on the concentration. In the next graph, what we're doing is increasing the concentration in aliquots of A. So this is different. We're not actually putting a certain amount of A in and letting that decrease over time. We're adding aliquots of A and observing the instantaneous rate at those points when we've added the aliquots to see what happens, and we're plotting data points here to observe the dependence of rate on the concentration. So we see that for a zero order reaction, even if we add more of A, we don't see an increase in the rate. So here we're plotting concentration versus rate. For a first order reaction, the more of A we add, we have a linear increase in concentration with respect to that amount. So we have a linear graph of concentration versus rate. For a second order reaction, again, we get an exponential curve where we see that the rate increases faster, much faster, the more of A we add. So we get an exponential increase of rate versus concentration. For a particular reaction in which A is forming products, a doubling of the concentration of A causes the reaction rate to double. What is the order of the reaction? The order of this reaction is 1 because the rate is equal to some K times the concentration of A to the first power. So doubling the reaction has the effect of doubling the rate. If we had a rate of, let's say, 4, then equal to some K times A to the first power, okay? Then if we doubled A, that would have the effect of changing the rate to 8, right? Because it would be like multiplying by 2. So the order of the reaction is first order. Again, the rate law must be determined experimentally, and to do this we use the method of initial rates, as we saw earlier with our graphs. If we have a reaction where A is forming a product, then we can plot the concentration of A versus rate. And so what we'll do is we'll increase the concentration in different aliquots. So let's say this is 0.1 molar, 0.2 molar, 0.3 molar, and so forth. So increasing the concentration in aliquots, and then we measure the rate at those aliquots. So we'll only measure the rate for a small period of time after we add a little bit of the starting material. So if we have a zero order reaction, the rate does not increase. In other words, if the rate is equal to the concentration of A to the 0 power, then the rate is not affected by increasing A. If the rate is equal to some K times the concentration of A to the first power, as we saw earlier, we get a linear increase in rate as we increase the concentration of A. If the rate is equal to some K times A to the second power, we get an exponential increase in rate as we increase the concentration of K. And these are the most common rate equation examples. We rarely see a deviation from this, but we will occasionally, and we do have at least one example where we'll see a deviation from zero first or second order rate equations with respect to one reactant.